I've had some questions over these, so I think maybe it is appropriate to address them. Here it says a certain culture of bacterium, strep A, initially has 12 bacteria and is observed to double every 1.5 hours. They ask to use this model here, which is a doubling model. Essentially, your T is your time, obviously, and A is your doubling time. Okay. So they ask here, can I write an equation or an exponential model in that form? So n sub 0 is 12, it's my initial amount. Now it's always times 2 because of the doubling. And now t is time, and we divide that by a, my doubling time, which is 1.5. So if you type it in that way, you'd be fine. You're seeing this solution here. Well, 1.5 is 3/2 of 12 times 2. T divided by 3/2, well, fraction divided by a fraction, multiplied by reciprocal, I get 12 times 2, and now it would be 2t divided by 3. So that's what they're looking for. That's nice. You can do it that way. A lot of people are doing this. They're saying, well, I should come down here and do it. N of t is equal to n sub 0 e to the RT. You're going through, okay, saying the doubling. So if I start with, 12 bacteria, e to the RT, I'm trying to double that, so it's going to be 24. The t we know to be 1.5, and we'll go through and try to find the rate of growth. So dividing both sides by 12 gives this to be 2, and then we're going to go e to the 1.5 r, ln both sides, so that's ln of 2. If I ln this side, it just gives me 1.5 r. So we're seeing ln of 2 divided by 1.5 is equal to r. And then they're writing for an answer, n of t is equal to my initial amount, 12, times e, now raised to the t times ln of 2 all over 1.5. And I'm typing that in right here, and it's telling them that's wrong, but they're using that then to come up with B and C, and B and C are right. So here's the thing, is that because of these two formats, one's doubling, and the other one is using kind of the half-life approach we've been using, but instead of being a half-life, it's a double life. If we use, doesn't really matter what calculator, I thought I had one open here. All right, so if I'm just going to see if I can pull open Desmos here. All right, so when I opened Desmos, everything kind of disappeared, but I think I can go from memory here. We had 12 times 2 raised to the, I believe it was 2t divided by 3 as one of our equations. Don't really worry too much about what t is right now. I'll come back and fix that. And the other one was 12e raised to the, I believe it was t times ln of 2 over 1.5. And again, don't really care what t is, but you can see there right now, just with t both being 1 in both these situations, those numbers are the same. Well, if t ends up being 4.3, they're both the same. So I believe now I'm just going to open another one of these. I don't remember what it did. Okay, so it's asking down here, so this is the exact same one, so that's good. So it's asking me for after 28 hours, what is the number of bacteria that I have? So then using that, let's take that slider and make it 28. I don't know how. Yeah, let me just type it in, 28. You see in both those, it gives me the same result that I'm looking for. Round it to the whole number would be, then that'd be a 2. So that's why it's showing you these two right, but this went wrong based off of using that base of E, and that's fine. I don't, to obviously get the point, hopefully you guys are going to take that information and kind of go back and fill in that one and fix that one. But overall, these are really the reasons we're trying to do this stuff, is to figure out these things. If I were to do part C again, what we're looking there is, if I'm looking at reaching 10,000, that would be my N of T. N sub-zero would have been 12. That was my initial amount. We had E. My R value that I found was ln of 2 over 1.5, and it would be solving for T here, okay, the number of hours. So I'm going to take both sides, divide by 12, so I get 10,000 over 12 is equal to E ln of 2 divided by 1.5 times T, and that's an exponent for E. So I want to get that variable out of that exponent, so I'm going to ln both sides. Okay, so I take ln of this side, take ln of this side. So taking ln of the left-hand side gives me ln of 10,000 over 12. Taking the ln of the right-hand side gives me just, this was the exponent, so it gives me T times ln of 2 over 1.5. So now I can, divide by that, or multiply both sides by 1.5 and then divide, but essentially multiply by this reciprocal. So it's going to give me ln of 10,000 over 12 times that reciprocal, so it'll give you a 1.5 up top, and it's going to give me an ln of 2 on the bottom. If you were to type that in, it will look for 14.6 here. So I just type that in. See if we do indeed get that. 1.5 ln of 10,000. I don't know if it knows what to do with commas. Divided by 12. And then that thing divided by ln of 2. You do get that 14.6 result. So that's question 1. I think the next question I had that I wanted to cover was 4. Okay. It says the half-life of strontium-90 is 28 years. So half-life, 28 years. All right, meaning I should be able to use that information to help me decide how long it's going to take to decay down to 60 milligrams. Okay. The question is, I've got 60 milligrams that I want to get to if I start with 100. Okay, so I got 100 is my initial. I want to get to 60. We have E to the R times T. Now the question is, how long will it take? So I'm looking for that T. R, remember, is not half-life. Okay, so the way that we're going to find R is we're going to come to the side and we'll say, okay, well, if I had 100 to start off with, I'm going to get down to 50 to be half-life. E to the R. Now T in this case would be 28, because that is indeed my half-life. So now divide both sides by 100, it would give me 1/2 here is equal to E to the 28R. ln both sides, I get ln of 1/2 over 28R. That's going to lead me to R equaling ln of 1/2 over 28. And that is the same thing as what we said in class. Whenever you're doing half-life, if they give you the half-life and you want to come up with R, it is always ln of 0.5 divided by your half-life number. Okay? So that is our R value that we're going to put right here. We're going to go ln of 1/2 divided by 28. Okay? And then times T, because that's what we're looking for. We're looking for this time T. So again, now all I got to do is divide by 100 to both sides. It gives me 0.6. E to that number, ln 0.5 over 28 times T, but T can be in the numerator here of that exponent. There you go. Ln of both sides, so ln of 0.6. Ln on the right-hand side, it's going to leave me T ln of 0.5 over 28. I can multiply by that reciprocal, so it gives me 28 ln of 0.6 over ln of 0.5. is equal to T. Calculate that real quick, should give me something close to 21. You see the if you're doing this on your TIA 3 or 4, that's fine, it's great. I'm glad that you can do that. But a lot of times, especially the older ones, as we talked about in class, don't always give you kind of the math print that we're looking for. So that I know typed in correctly because it matches what I wrote by hand. So we get 21 as the closest year. All right, so do one more of those half-life questions. I'm not sure which one was the next one, 5 or 6. It says something about, there we go, going down to 97% of a sample to decay. How long will it take for 97% of a sample to decay? Well, half-life is 50%. But what I need you to understand is that the rate of decay is constant. So if it takes me, so right now, if we're doing ln of 0.5 over my half-life, okay, that is constant. That's R. That is constant all the time. So it doesn't matter if I'm doing half-life or 97th life, 97%, 0.97 of the duration of the life of this object. It does not matter. That number R has to be constant. So kind of keep that in mind as we work through this. It says radium has a half-life of 30 seconds. Okay, so just to kind of expedite things, we could go through this process again, N sub 0 E to the RT, go through that, plug in, okay, well, if this is going to be my initial amount, don't know how much I start with, maybe I start with 100, when I get half-life, it'd be 50, so I get 1/2 is equal to E to the RT, but T, because it's half-life, in this case, the time is 30 seconds, so we could do that whole process. To find R, but again, I think it's easier to say, we've done this enough, that R is ln of half divided by my half-life. So that's my R. So then it asks, okay, what does it do, or how long does it take to go from 97% of a sample to decay? I don't care what I start with. If I start with 100, okay, the question is how long will it take for 97% of a sample to decay? So if I start with 100, if that's N sub 0, then after my time duration, okay, that I'm looking for, or whatever my solution is, I should be down to 3. Okay? Because if 97% of my sample decayed, 3% is left over. If I started with 100, 100 to 3. Now you can use any number right here you want to. You know, I want to use 54. If I start with 54 grams, okay, I would have to figure out what 3% of 54 is, and I can put that there. I just think, I always like to, if they give me a percentage, I always like to start with 100. So I've got N of T, N sub 0, E to the RT. Okay, so NT, so we're looking for 3 to be, now this is 100. We would have ER, ln of 0.5 over 30 times T. So when I divide that out, that's going to give me, dividing by 100 gives me 0.3 is equal to E ln of a half divided by 30 times NT, ln both sides, so ln of 0.3. When I ln both sides, give me that. T can go up top, so T ln of 1/2 divided by 30. Multiplied by that thing's reciprocal, so it gives me 30 ln of 0.3 divided by ln of 0.5. That should be the time that it takes to get down to 97% of what's left over. So let's see what that time is. Should be 152. So when I get 30 ln of 0.3 divided by ln of 0.5, what did I do? Did something wrong? 52, 152, 30. Oh, my apologies. 3. I put 3 here. It should be 0.03. That's my fault. So let's see here. That fixes things. Okay. 97% is 0.97. 3% is 0.03. So that's my fault. 0, 0, 0. You can do the same thing in the next question. I think I'll leave this for you to finish on your own here with this one. Actually, let's do this one. This one's useful too. It says if 250 milligrams of radioactive element decays to 240 in 36 hours, find the half-life of the element. Okay, so we're talking now.